Welcome to the 63rd Annual Undergraduate Research Symposium of the American Chemical Society, New York Section Student Activities Committee. First, I want to thank you all for being here so early on a Saturday morning. The URS is a wonderful opportunity for our students, and we thank you all, mentors, family, friends, and our sponsors for your support of them. We have a number of important people to welcome you here this morning. But first, we want to especially thank our sponsors of this symposium, without whose support we wouldn't be able to give you all the treats that are in store for you today. Thank you to our host, Queensborough Community College. From the president to the buildings and grounds, as you look around our campus today, you'll see why we're extremely grateful for all of the internal support of our host this year. Thank you to Pepsi, to the Louis Stokes Alliance for Minority Participation of CUNY, to the Office of Research, the Office of the Vice Chancellor of Research of CUNY, to Cengage, to Anasazi, to Wiley, to the Royal Society of Chemistry, to McGraw-Hill, to Kaplan, to Pearson, to On Assignment, and of course, to the American Chemical Society, New York Section. I'm going to turn things over to co-chair Dr. Paul Sedaris, and he will introduce our speakers for this morning.
Thank you. Good morning, everyone. We'd just like to, before I introduce our speakers, encourage everyone to browse our sponsor tables that will be in the Student Union where we will have lunch. I'd like to first thank President Diane Call, President of Queensborough Community College, who was very supportive of this event. Unfortunately, she was unable to come in this morning to give some opening remarks. So our first speaker is going to be the current chairperson of the New York section of the American Chemical Society, Dr. Paris Zvoronos.
Thank you, Dr. Sedaris. So, good morning. Sorry, I didn't kill anybody. So welcome to Queensborough and welcome to the ACS New York Section, URS, which is one of the most prestigious and long-time undergraduate symposia in the country. And why not? We can also say of this world. Through your dedicated mentors, you students achieved a lot. Your mentors deserve a great round of applause because they chose to work hard. And both you and them had absolutely not a particular significant personal gain. Your mentors were driven by pure enthusiasm for teaching, and you chose to go through this experience that many, many times had failures. Nevertheless, you stood up on your feet and you delivered, and today you have the PowerPoint to present. So in 1910, there was a British poet by the name of Rudyard Kipling who wrote a poem whose title was If, which is often compared to the 700th verse of the Gita, a Hindu scripture that is part of the epic Mahabharata. It is believed that Kipling wrote this poem for his son. So I'm not going to recite the whole thing, so I chose only a few of those verses that personally personify the tough times you had with your research and how they led to your maturity as young human beings and professionals. So here we go. If you can keep your head when all about you are losing theirs and blaming it on you. If you can trust yourself when all men doubt you, but make allowance for the doubting too. If you can meet with triumph and disaster and treat those two impostors just the same. If you can lose and start again at your beginnings and never breathe a word about your loss. Yours is the earth and everything that's in it. And which is more, you'll be a man, my son. And I should add, a lady, my daughter. So wishing you the best in your endeavors. Thank you.
Thank you, Dr. Zvoronos. Next, I'd like to introduce the chair of the chemistry department here at Queensborough Community College, Dr. Chitosan Karimi.
Good morning. I've actually been pretty sick this whole week. I was ready to call the ambulance to bring me here today, but I'm very happy to be with you today. Welcome to Queensborough. This is actually a third time we're running this event. First time was in 2004, and the second time was in 2008, which we also ran the Mid-Atlantic Regional Meeting. All these events went quite successfully, and we are very proud to present to you the 63rd Undergraduate Research Symposium today. I know for student presenters today, you've worked really hard on your research work, many hours, day after day, and have obtained your results, have spent a great deal of time doing your PowerPoint presentations. So that's already a big accomplishment, and we all congratulate you for that. So relax, make your presentation, and have a wonderful day.
Thank you, Dr. Karimi. At this time, Dr. Lal Ramnarayan will do us the honor of introducing our keynote speaker for this morning. I'd just like to remind everyone, can you please turn off your cell phones or put it on vibrate for the duration of the talk. Thank you.
Thank you, Dr. Sidaris. It is indeed an honor and a pleasure to introduce our keynote speaker, Dr. JaimeLee Rizzo, a dear friend of mine from graduate school and a close colleague. She's from the Department of Chemistry at Pace University and an alumna of Queensborough Community College. Further, she conducted research here as an undergraduate, like so many of you here today. It wasn't math, but she soon converted. She graduated as valedictorian with an associate's in science from Queensborough in 1995 and was the recipient of numerous awards. She then transferred to Queens College to pursue a bachelor's in chemistry and graduated there in 1998 with her bachelor's. While at Queens, she continued conducting undergraduate research, this time in organic chemistry with Dr. Robert Engel. Dr. Rizzo's research was funded as an undergraduate research assistant through the Lewis Stokes Alliance for Minority Participation at CUNY, a sponsor of this symposium. After her bachelor's, she went on to pursue a PhD in chemistry at the Graduate School of the City University of New York. Continuing to work with Dr. Engel on the synthesis of polycationic organic salts. Dr. Rizzo completed her graduate work in 2001 after just 3 years, with a total of 14 publications and numerous presentations at national and international meetings. That same year, she started her tenure-track assistant professor position at Pace University in the Department of Chemistry. Her research at Pace has been on the development of antimicrobial surfaces and has led to a number of patents, publications, and presentations. In addition to her exciting research, Dr. Rizzo is also a very active member of the American Chemical Society New York section. In 2012, she was the chair of the section, and she has been a committee member since 2005, co-chairing the Student Activities Committee and the Symposium from 2005 to 2010. She has also served as coordinator for the committee that coordinates National Chemistry Week and coordinator of Chemists Celebrate Earth Day. Dr. Rizzo has always been active as a research mentor to undergraduate students, even while she was a graduate student herself, mentoring about 9 to 12 students before she obtained her PhD. Her research group at Pace University consists of numerous undergraduate students that are always active participants in this symposium, presenting at least one talk per year. At this time, it gives me great pleasure to introduce our keynote speaker for today, Dr. JaimeLee Iolani Rizzo.
Paul, can I have your assistance here for a second?
Sure.
Great. Okay. Hi, good morning, everyone. Can you hear me back there? Okay. So first of all, I'd like to thank the coordinators for the symposium for inviting me here. It's always such an honor, and it's always so warming to come back to Queensborough. I'd like to especially acknowledge my mentor here from Queensborough, Dr. Paris Foronos. He's just been supportive since the time that I've been here from Queensborough to this day. So thank you all. Now, for some time, our laboratory has been involved with the synthesis and investigations of these polycationic organic salts. So these salt synthesis, in fact, goes back to my undergraduate days, as Sharon mentioned, at Queens College. And during that time, we found that these salts, some of these salts, they bear antibacterial and antifungal characteristics. And now, it wasn't until my starting at Pace University in 2001, where we started to think about, well, what happens if we take these salts and bind them onto a given surface? Would that render a surface antimicrobial as well? So what's the significance for these antimicrobial surfaces, or as dramatically I like to refer to them as constructing killer surfaces? Well, prevention of cross-transmission of organisms is essential to preventing outbreaks of hospital-acquired infections. The demand for antimicrobials is evidenced by recent studies that indicate cross-contamination is a leading cause of patient morbidity, resulting in hospital death. While hospital-acquired infections are becoming increasingly common worldwide and occur in more than 2 million hospitalizations in the U.S. per year, the burdens these infections place on our healthcare system can be divided into the cost of human lives, quality cost, and financial cost. The human cost is over 99,000 deaths per year in just our country, which represents a 5% death rate for hospital-acquired infections. Quality costs include increased intensive care unit stays by 8 days and increased average hospital stay between 7.4 and 9.4 days. The total dollar costs added to our already strained healthcare system are between $4.5 and $5.7 billion per year. Specifically, methicillin-resistant Staph aureus has become endemic, even epidemic, in many U.S. hospitals. Now, the sales of medical antimicrobial products reached over $20 billion just in 2009. The sales of these medical antimicrobial products are expected to grow between 7 and 11% throughout this year. There is an obvious need for antimicrobial products that will prevent cross-contamination in the hospital setting. So what we've been successful in doing is generating a variety of surfaces that render those surfaces permanent antimicrobial characteristics. These surfaces include fabrics, so cotton-based material. Particularly, this technology can be used for hospital and hotel settings, as well as for the military. We've also generated antimicrobial wood. Now, that, of course, can be used for the construction industry, for anti-rot, and for anti-termite. We've been successful at synthesizing antimicrobial wound dressings. And of course, this can help in the prevention of hospital-acquired infections, as well as antimicrobial paints. This can be used in hospitals and hotel services. Also, we have technology for antimicrobial flexible plastics. This can be used for coverings and storage facilities, gym equipment, as well as the military. So we've acquired, I'm going to discuss first two methods. We've acquired two patents, and they use different type of methods. The first method here is used to modify natural-based materials, such as cotton cloth and paper and wood. So this is a very simple two-step procedure where, it's time to use the pointer, where we take a free hydroxyl site, let's say from your cellulose-based material, and activate it. We call this the activation. Why? Because we're converting hydroxyl to tosylate, which we then generate a very good leaving group. So that's the first step, is the activation of your surface. The second step involves attaching this cationic lipid that's previously prepared. So we generate an array of different cationic lipids, and simple SN2 reaction displaces the tosylate, so you form a covalent bond between that carbon and nitrogen of your surface. Now, it's these cationic lipids that was determined during my undergraduate days that already bear this antimicrobial activity. So what's new was this last step here, is attaching it to a surface. Okay, so the second method is for synthetic materials. Materials maybe that don't have a free hydroxyl group that can be activated, and then you perform that covalent attachment. Here we use, here's one example, a modified cationic molecule that's embedded in the surface by either melting or painting it onto a given surface. So this molecule is, of course, based on glycerol, but we use the same type of activation step followed by displacement. And here I'm showing that what we call DABCO C16 hydrocarbon. So our DABCO hydrocarbon technology has been tested against a number of bacteria, gram-positive bacteria, gram-negative bacterial spores, as well as fungi. Our cotton cloth has also been tested by the U.S. Army at Aberdeen Proving Grounds in Maryland. And here we're showing Bacillus anthracis spores that demonstrate a log4 reduction after 2 hours of exposure to the modified cloth material. So if you look at the graph at the top here, that's of course the blank, unmodified cloth, right? So there's no reduction in the anthracis spores. Whereas here, That's the modified cloth that noticed the reduction of the spore. Our technology was also tested with the United States Department of Agriculture. So what we did here was take their paper, and using our DABCO technology, they did their testing and they found that it prevented mold and fungal growth. Yet all the while it permitted the germination of seeds, which is important, right? You want your seeds to be able to grow, although no mold is growing. Weyerhaeuser Corporation, we worked with them as well. We took Weyerhaeuser's different type of wood material, which are cellulose-based, and we treated it with our DABCO technology. Weyerhaeuser found that it prevented mold and fungal growth on the surface. And here's something that we didn't expect, that the modified wood was resistant to termite attack. Okay, so this slide, let's look on the left. On the left, we see E. coli, about 1 million cells that was added to the surface of brown paper, either treated or the blank. So the paper on the right, that's of course the modified paper, right? You see no E. coli growth surrounding the paper, whereas on the left is full growth of E. coli, untreated, that's the blank paper, right? And then this Petri dish on the right is with Staph aureus. This both comes from the USDA, that's their specific paper that they use. So again, same type of setup, but this time with Staph aureus. And again, we see on the right that modified paper, no growth of the staph, and full growth here surrounding the blank. Okay, so cationic lipids as antimicrobials are not new, but our method of organization of these cationic lipids is new. Microbes are killed through the disruption of the cell wall rather than through a metabolic process. The permanence, though, depends on the mode of association with the surface. So in the next few slides, I'm showing some schematic here of the association of our modified material. So say this here represents a treated, let's say, cloth material, okay, where you have that DABCO lipophilic chain attached. It's a covalent bond to the surface. So notice how the lipophilic portion of that modified cloth is associating with the outer membrane of the cell, right? Oh. And then we see it's actually piercing through that lipophilic portion of the outer membrane until it starts to drag into the membrane that quaternary ammonium site, right? That quaternary ammonium site from that DABCO ring, which results in actually the lysing of the cell. I love this photo. It's very scary looking, right? So most recently, our modified cloth material has been tested against T4 bacteriophage virus. So it was found that a different type of DABCO moiety, so we're talking about not just one DABCO unit with a long lipophilic chain, we're talking about 2 DABCO units with methylene groups sandwiched in between them. So that's what we call a DABCO hydrocarbon DABCO molecule. So this DABCO hydrocarbon DABCO molecule, covalently bound to cotton cloth, has been shown to reduce the number of T4 bacteriophage virus particles available for infecting bacteria after incubation. Using a plaque assay, we have shown that the cloth removes the virus from the solution it was in and holds it, rendering it incapable of infecting bacteria. So this work is actually in the process of being written up. This is quite new. So a little background, there's not too many of us who are maybe keen on our biology, nomenclature about viruses and virions, so I wanted to give a little general review about what a virus actually is. So a virus means Latin for poison. The virus contains some of the structures and exhibits some of the activities that are common to organic life, but they're missing many of the others. In general, viruses are entirely composed of a single strand of genetic information encased within a protein capsule. Viruses lack most of the internal structure and machinery which characterize what we call life, including the biosynthetic machinery that is necessary for reproduction. In order for a virus to replicate, it must infect a suitable host cell. So viruses exist in two different states, dormant without a host cell. In this non-living state, viruses are referred to as virions. Virions can remain in this dormant state for extended periods of time. When the virion comes into contact with the appropriate host, it becomes active and is then referred to as a virus. It now displays properties typical of living organisms. For example, it can react to its environment and direct its efforts towards self-replication. Here's that guy again. Bacteriophage T4. That comes from the Greek word meaning to eat. It's all about the Greeks, yes, Dr. Sfodonos. A bacteriophage is a virus which infects bacteria. The bacteriophage T4 is a virus which infects E. coli. Okay, so T4 exemplifies the life cycle of viruses. It exists as an inactive virion until one of its extended legs comes into contact with the surface of an E. coli. Sensors on the ends of its legs recognize binding sites on the surface of the host cell, and this triggers the bacteriophage into action. The bacteriophage binds to the surface of the host, punctures the cell with its injection tube, and then injects its own genetic blueprint. This genetic information subverts the host cell's normal operation and sets the cell's biosynthetic machinery to work, creating replicas of itself. These newly created viruses escape from the cell and then float about dormant until one happens to come into contact with a new host cell. So this graph here shows our cloth. Okay, so we have all these different cloths. Notice with this one, it's a covalent bond to a DAD-CO-C12. This one is with a DAD-CO-C16. Here's the di-DAD-CO with C6 sandwich in between, with C4 in between. And here's other type of di-DAD-CO modified cloth. So what this is showing is a percent reduction of virus plaques. So obviously the most efficient modified cloth is the JLR22. Guess who made that one? That was recently done. That is over 90% effective, right, in reducing the virus plaques. As is this di-DAD-CO-C6 and di-DAD-CO-C4. The least effective of the modified cloths comes, looks like it's a di-DAD-CO-C3, where it's only a little above 10% reduction, right? Okay, here's more new recent work and findings. So additionally, we have recently shown that a different novel DAB-CO hydrocarbon molecule prolongs the life of cells that have been exposed to the influenza H1N1 virus. Sasan, maybe you should have been made aware of this last week. When cells are exposed to virus, they typically die within 3 to 4 days. However, when virus is first exposed to the DAB-CO hydrocarbon cloth, the cells can survive up to 6 days. Okay, another graph. This graph, days survival after exposure to the virus. So it's been incubated with modified DAB-CO cloth. So we can see then that the most effective modified cloth comes from DAB-CO C12, 14, 16, and 18, right? where in the red, that red bar shows H1N1 exposed cells, and they survive up to 6 days. One of the least effective is this DAPCO clock. So it's just a clock, and all it is covalent binding onto a DAPCO unit. No lipophilic functionality, no di-DAPCO, just a DAPCO unit. We also have acquired 2 other patents for similar type technology. One of them is called embedding antibiotic compounds into solid polymers. So this invention involves antimicrobial compositions consisting of a polymeric material and embedded therein an antimicrobial compound. Another one, which I've just discussed with our viral studies, is a patent for antiviral compounds. This invention relates to novel antiviral compounds which are covalently attached to the solid macrosurface. Over the years, we've also worked with Johnson & Johnson Wound Management Division, and we've acquired 3 patents with them. Antimicrobial polyurethane foams, antibacterial polymers, as well as pH-dependent medicinal compositions. So what is antimicrobial polyurethane foam? Well, they have a number of medicinal uses, like in the medical devices and pharmaceutical compositions. The foams are prepared by reacting particular diisocyanates or isocyanate-capped prepolymers with suitable chain-extending compounds having an amine, that's where we come in, and or alcohol multiple functionality. Chain-terminating compounds such as monoamines or monohydric alcohols may be included in the reaction mixture. Water may be included in the reaction mixture since it reacts with isocyanate to liberate CO2 for foaming up that mixture. So we have a couple of other ongoing projects in our lab. We've also been working on the synthesis of compounds that will target potassium ion channels. This doesn't relate to any type of killer surface, but it's another project that we have in our lab. We also have been modifying naturally derived materials and to try and formulate a new surface that can serve as a wound dressing. So with my collaborators, Jeff Abbott, who's now at UC Irvine, he's the vice chair of Department of Pharmacology there, and my mentor, Bob Engel from Queens College, we have acquired a patent for methods for modulating potassium ion channels. So what is an ion channel? An ion channel is pore-forming proteins that are responsible for the gradient across the plasma membrane of cells. Ions can't move freely across the cell membranes. They need to enter or exit a cell through pores created by the ion channels. Ion channels open and close in response to particular stimuli, such as ions, cellular factors, or changes in electrical voltage. Channels are selective for specific species of ions, such as sodium, potassium, and calcium. Ion channels are significant components in a wide variety of biological processes that involve rapid changes in cells. Ion channels are therefore a frequent target in the search for a new drug. Here's a new drug that we synthesized. Notice it's a di-DAPCO hydrocarbon chain, right? We call this JC279.3 alpha. So this novel compound, you know what that means, my numbers there. So JCC was my previous last name, so I made this. And that 279 stands for, that's the 279th compound that I made. And 0.3 tells me that it took me 3 different techniques to purify this compound. And that alpha tells me that, okay, this was in the solid and not the aqueous layer. So I have my own method to my madness. So this novel compound shows that it increases mouse skeletal muscle contractile force. It's really an exciting advance toward the goal of developing drugs to combat muscle weakness, such as muscular dystrophy. Here are 3 other compounds that we've synthesized. It's a DABCO C16, DABCO C12, and that last molecule we call a paraxylyl didabco, based, of course, on paraxylene. These 3 compounds are found to specifically either open or close potassium ion channels. So getting back to our constructing killer surfaces, we've been working with chitosan. So chitosan is a biopolymer that's derived from chitin. It's found in crustacean shells and in strains of yeast. It can be synthesized by the N-deacetylation of chitin. So if you take chitin and you throw in some acid, what you can isolate is glucosamine. But if, on the other hand, you throw in base, what you can get out of that is this deacetylation of chitin, which is chitosan. So we work with chitosan, and we work to modify that chitosan. So we've done several things with chitosan. We have covalently attached a DABCO chain to it, which results in positively charged sites, which coats the microbe and interacts with negatively charged membrane surface. This alters then the permeability of the cell membrane, causing osmotic imbalances and eventually inhibition of growth and leakage of electrolytes such as potassium ions. So there are a number of applications of chitosan that's out there. Well, they're used in biomedical field, including for wound dressings. Chitosan reduces scar tissue. It can form a protective film. It's non-toxic to mammals as well as to the environment. It's biodegradable. It's easily modified and biocompatible. So chitosan is used for water purification. It's used in the fabric industry, such as starch. It's used in treating inflammation, Crohn's disease, which is a type of IBD, and kidney failure. It's used in batteries and photography. Chitosan is also used in the medical field for scaffold and tissue and bone engineering. So if we look at the structure of chitosan, you can see that the C3 and C6 hydroxyl functionalities of chitosan, as well as the C2 amine functionality, we can easily manipulate these. When we did our work into covalent binding of an antimicrobial to chitosan, it was actually at the C6 hydroxyl group where we were targeting. So again, we were forming a new carbon-nitrogen bond to chitosan. So one of our latest work, and in fact my student will be talking about this work today, Angelique, and Angelique wants everyone to show up in her talk. Our latest work involves oils, various oils that are infused into chitosan. These are some of the oils that we've been preparing and have been tested. They include propolis, ginger, yarrow, black elderberry, turmeric, thyme, and neem. So I'm going to talk a little bit just about what these oils are and their significance and why we chose them. And there are others that we have other ideas as well, but we haven't started those yet. So here's black elderberry. Now, elderberries have been used for their medicinal benefits for thousands of years throughout our country, Europe, Western Asia, and North Africa. In the Middle Ages, it was considered a holy tree due to its ability to improve health and longevity. So black elderberry has antioxidant type effect. It can act as a diuretic, a laxative. It's immune boosting. It's an anti-inflammatory. And it's been shown to reduce influenza A and B. Here's yarrow. Now, the Navajo considered it to be life medicine. They chewed it for toothaches and poured an infusion of the yarrow oil into their ears for earaches, to treat earaches. Yarrow's been found to heal inflamed wounds, rashes, cuts, eczema, scars, and burns. It can also promote hair growth. So many of you are probably most familiar with this oil. It's ginger oil. So the peculiar hot and pungent taste of ginger can be attributed to the presence of an acrid compound called gingerol. Most of the health benefits of ginger are actually due to the presence of gingerol. Ginger oil is composed of 90% Swiss okay, you could read that, which are responsible for anti-inflammatory, antibacterial, and other healing properties. When ginger oil is applied topically or inhaled, it has a warming and energizing effect. Turmeric. Turmeric has become very popular in the last years, right? We're all a little familiar with turmeric. So the volatile oil fraction of turmeric has demonstrated significant anti-inflammatory activity in a variety of experimental models. Even more potent than its volatile oil is the yellow or orange pigment of turmeric, which is called curcumin. Curcumin is thought to be the primary pharmacological agent in turmeric. In numerous studies, curcumin's anti-inflammatory effects have been shown to be comparable to the potent drugs hydrocortisone and phenylbutazone, as well as over-the-counter anti-inflammatory agents such as Motrin. In fact, as an aside, I give my dog turmeric capsules because it helps for inflammation. Thyme oil. A lot of us are familiar with thyme, the herb. So the benefits of thyme essential oil have been recognized for thousands of years in Mediterranean countries. This substance is also a common agent in the Ayurvedic practice. Ayurveda is a type of complementary and alternative medicine that originated in India over 3,000 years ago. The oil has proven to be antibacterial, antispasmodic, anti-rheumatic, and used as an expectorant. Propolis oil. Propolis is a natural resin collected from the buds of conifers and other trees by honeybees. It is used by bees to seal walls and strengthen combs of hives, as well as to embalm their dead invaders. The term propolis comes from two Greek words, pro, which means before, and polis, which means city. This ancient term came into being centuries ago when an early Greek student of nature happened to notice that honeybees use propolis to narrow the openings into their cities or hives to keep out their unwelcomed intruders. Many sources attribute the word propolis to Aristotle. Thousands of years ago, ancient civilizations used propolis for its medicinal properties. Greeks used it to treat abscesses, Assyrians put it on their wounds and tumors to fight infection and help the healing process. Egyptians used it to embalm mummies. And we have neem. Neem, well, here's the evergreen tree that's endemic to India. Neem can be applied directly to the skin to treat head lice, skin diseases, wounds, and skin ulcers. It's used as a mosquito repellent and as a skin softener. It's also used as a natural insecticide. So applying neem, it's been found, the neem leaf extract gel, to teeth and gums twice a day for 6 weeks may reduce plaque formation. This is not our work. This is just background information of neem. It also might reduce the number of bacteria in the mouth that can cause plaque. If you've ever smelled neem oil, though, it doesn't smell very pretty. Okay, so what we're showing here on the left is the first step into preparing this chitosan material. So we generate this chitosan gel that's stirring in those large beakers. And on the right, what we end up doing is pouring that chitosan gel into petri dishes, and we infuse into them all these different type of oils. And we've already talked about all these oils that we've tested. That we have infused into the chitosan. Okay, so the petri dish on the far left, that's our control. So here we have turmeric, it's just the oil. Turmeric, propolis, ginger, and thyme. And it's been shown that all of them has an effect against the yeast Saccharomyces cerevisiae. And this is just the back of the same plate. Okay, so they all inhibit Saccharomyces growth. Now this petri dish is showing the chitosan sheets that's infused with, well, this one is turmeric, this one is propolis, and this is the blank. Turmeric on this plate is the only one that's been shown to inhibit Saccharomyces growth. The blank chitosan, note, does not inhibit any growth of the yeast. So this is most current work. In fact, I think my student got the results just maybe a week or two ago. Okay, so this petri dish here on the far left, that's black elderberry, here's neem, and here's yarrow. So again, it's just the control, it's just the oils. The neem absolutely had no effect on the growth. Black elderberry inhibited growth by 80%, and the yarrow by 90%. And that's, again, the back of this petri dish. On the far right here, we have black elderberry on the top. The blank is on the left, which is negative, so full growth of the yeast. And then the right is the yarrow, which shows some inhibition, as well as the black elderberry chitosan sheet showed inhibition. And my student will go into detail during her talk about the synthesis of these and more about the results. So in the past, we've also modified chitosan by infusing hemp oil. Well, hemp oil is a fatty acid that, in hemp oil, there's fatty acids that make it beneficial in a variety of skin and hair care products. Hemp seed oil contains linoleic acid and linolenic acid as its major omega-6 and omega-3 polyunsaturated fatty acids. When hemp oil is applied to the skin, it nourishes the skin cells and has anti-inflammatory properties. So if we look at this petri dish here, that's our chitosan with hemp oil infused into it. And this picture is showing the flexibility of this new surface. See, it's very pliable, right? We've also worked with gelatin A, modifying gelatin A with Dabco-type hydrocarbon compounds. So gelatin is a protein produced by partial hydrolysis of collagen extracted from the bones, connective tissues, organs, and some intestines of animals such as domesticated cattle, pigs, and horses. So where can we identify that we can modify gelatin? We already identified that on the chitosan, it was that C6 hydroxyl group, right, that we can modify to form a new covalent bond to chitosan. Here with gelatin A is that secondary hydroxy group, this of hydroxyproline moiety. So again, we just activate it with, say, a tosylate, and then perform an SN2 with a Dabco hydrocarbon chain. Both the gelatin A as well as the chitosan with various Dabco hydrocarbon moieties bound to it have proven to be antibacterial and antifungal. So they're both highly effective, depending upon that cationic salt that's covalently attached. Not all of them are effective. So today, I've talked about these killer surfaces, right? There are more to come. I'll talk about that next time I'm invited back to Queensborough. So carbohydrate-based surfaces. where we activate that hydroxyl group. That includes cotton cloth, wood, right, paper. We can also work with proteinaceous-based surfaces. Why? Because proteins contain amino acids that have hydroxyl groups, such as serine or threonine. So we can activate those hydroxyl groups and then covalently attach on a dab comoiety. We've also been able to generate antimicrobial materials to infuse into paints, as well as infusing or melting some of our compounds into plastics, so you can work with flexible plastics. I've talked extensively about Chitosan, and now we're working with Chitosan with natural oils infused to it. And gelatin, which I just discussed, with that hydroxyproline functionality that we can work with. So I'd like to acknowledge my collaborators, Dr. Bob Engel, my mentor from my undergraduate days at Queens College, Dr. Karen Melkonian, our biologist at CW Post LIU, who's done most of the bacteria and fungal testing, and she's done all the latest viral testing on our cloth materials. Dr. Jeff Abbott from UC Irvine, he has nothing to do with my killer surfaces, but he had to do with the potassium ion channels, if you recall. And Dr. Chitosan, biochemist from Pace University, who's recently been testing our chitosan that's infused with those various natural oils. So she's been doing all those yeast studies. And here's a beautiful picture of us last time we were here at Queensborough. I gave my talk. That was back in May 17th, 2008 at the 56th Annual Undergraduate Research Symposium. And look, guys, we haven't even aged a bit. It's amazing. And I want just to point this out. So I'm loading up my talk, right, to bring it here on this little flash drive. And just this morning, I hadn't noticed this for years. Which flash drive am I using? New York, ACS, URS, May 17th, 08. I've had this guy for 7 years. And then I happened to find this one because, what happens when you give a talk? Anything can go wrong. So I sent my talk earlier to Sharon. I have my talk on 2 flash drives. And what's the other flash drive that I grabbed? Queensborough. This is from MARM, right? And that's also 7 years ago. So I'd like to thank all of you here, and I'm hoping that the sun's out now, so we can all go into, in front of that library and take another beautiful photo. But thank you all.
Thank you, Dr. Rizzo. We have some time for questions. Any questions?
How long does these surfaces last on exposure?
The permanence of the antimicrobial agent to the surface, depending on the surface and how you wash the surface. So unfortunately, you'll cleave off any that antimicrobial activity. You cleave off that carbon-nitrogen bond if you throw it with some Clorox in there. It's not good, right? I mean, in the hospital settings, they Clorox everything. Everything's bleached. Any strong base will also cleave it off. You get an elimination type reaction. So that's why I'm not a billionaire right now. I'm still here. But we're working on it.
Hi, Jaime. Regina Sullivan from Queensborough Community College.
Hi, Regina.
How are you?
Good.
Thanks for the great talk. Do you happen to remember what cell line you used to test the H1N1?
I'll have to get back to you on that. I didn't do any of the testing. That was Karen Melkonian.
Oh, okay. Really very interesting. And maybe we'll talk later.
Oh, great.
Thank you. Take care.
Regina and I go back to Queens College in grad school.
Hi, thanks for the talk. I'm from Lamapur College. My name is Seung-Sub Kim. I just have a question. Like when you talk about the killer surface of bacteria, I see different types of the bacteria you're dealing with. But recently, we know there's some beneficial bacteria which is causing trouble because it's not there. So, do you have any specificity study you're doing for the surface?
Yes, and I didn't go into detail about all the different type of bacteria. So say a Dabco C12 can be affected to some only gram-negative bacteria, whereas a Dabco C16 that's bound to a surface is against certain gram-positive bacteria. So yes, absolutely. But we've also made hybrids of surfaces, not just one type of adjunct that's added onto a surface. So in other words, I could put 3 different types of cationic lipid onto a given surface, right? 30% of each type. And so if we wanted a full kill of everything, you put it all on. So it kills against all the different bacteria that you want. Save our friends, yeah. Okay.
Hi, my name is Abbas. I'm from York College, CUNY. My question is, have you tested the effect of these killer surfaces on human cells?
No. Are you volunteering? Not yet, no.
Sure. My name is Omar. I'm from NYU Polytechnic. And I have 2 questions. Do we know the mechanisms by which the hemp oil and the thyme and elderberry, how they affect the bacteria for therapeutics? Any of them? And also, are those Dabco cations self-assembled onto the surfaces?
Say that second part again?
Are they self-assembled onto the surface?
Self-assembled, no. So what we're doing, remember, we're just targeting usually, in Chitosan you have, like, say, a C3, C6 hydroxyl, right? We're just going to target the primary hydroxyl. It's much easier to activate it at the primary versus a secondary, right? So it's not really self-assembled, and we take ratios into account as well, right? Your first question about the oils and the mechanism, no. And that you would have to speak with the naturopathic type physician. Very interesting, though, right, with the natural oils.
Yeah. Thank you.
Hi, my name is Haley Crabtree. I'm from Drexel University. And I'm curious how your work applies to the hygiene hypothesis, where, our world is kind of too clean, and so we're getting lots of these opportunistic infections. So in regard to the hospital application, how do you feel this will affect C. diff infections or things like that?
So, and I haven't even brought up C. diff, but a lot of our salts that are connected to modified surfaces are effective against C. diff. So, I am more into not killing all of our friends, as our friend there has said, right? That's why our research now is going more into natural type antimicrobial. So I'm investigating a natural type of surface. But there are instances, like say diabetic ulcers, right? You need to kill everything, right? So drastic measures requires drastic steps in some instances.
Are there any other questions? Oh.
It's Tommy Lee, NYU Poly. You had the termite and your product. Did it kill the termite, or did it starve the termite? Did they avoid the wood?
So what Weyerhaeuser found was that it deterred. It did not kill them. It deterred them. So similar type of reaction or behavior towards the insects with, say, neem oil. So it doesn't kill them, but it just deters them.
Then a follow-up question, I'm sorry. So you don't know if your product actually killed the bacteria in their stomachs or in their intestines, I should say.
Kill the insects?
No, the termite. The termite feed on the wood because of the bacteria colony.
Yeah, we don't know.
Okay.
We haven't done that testing. That's Weyerhaeuser.
Hi, good morning. My name is Vaughn Green, and I attend City College. I had a question about the ion channels specifically. The compound that you made, does it attach externally to the channel, and what does it actually do to the channel?
Repeat the first.
The compound that attaches to the ion channel, like where is the location that it would attach on the ion channel? And then what does it actually do to the channel to cause it to retain contraction?
Open or close specifically?
Yeah.
It's dependent upon, again, the different compounds. So I showed you only 4 compounds, right? That didatical hydrocarbon and some of the other monocationic salts. So it's depending upon the compound, whether it'll open or close it. That JC279.3 alpha, that one specifically opens the potassium ion channels. So the association with it, you could talk to my pharmacology collaborator, or I'll give you links to the patents and publication.
Okay. Thank you.
My students don't want to harass me? I'm surprised. You're always harassing me.
Any other questions?
Hi, Rachel Van Beek. I'm from Benjamin Moore and Company, the paint company. I just have a question if you have used any of this technology in a latex type coating.
Do we apply it to latex? Have we applied it to latex? Yes, it could be just infused into the paint.
Okay.
Absolutely. I'm so glad Benjamin Moore is here. We need to talk after.
Yes, we do. Thank you.
Any additional questions? Going once? Going twice?
Okay, let's thank the speaker again for a wonderful talk.
So thank you, Dr. Rizzo, for such a stimulating talk. And thank you for still being so enthusiastic about these events, about undergraduate research. At this time, we would like to present Dr. Rizzo with this plaque of appreciation from the New York section of the American Chemical Society Student Activities Committee. Co-chairs?